Okay, working on inverse functions, they've given us this equation. It's the equation of some quadratic. And they asked us to find the inverse and to figure out if it is a function. Okay? In order to do this, the problem we have right now is our y, when we go to put the inverse function in, what we do is we substitute y into the x value. But we have two x values here. Okay? This is a quadratic and it's technically in standard form. Okay, standard form, I'm just going to write it all in red here. It's usually written like f at x is equal to ax squared plus bx plus c. Okay? There's also factored form, which is f at x is equal to a x minus r x minus s. And then finally there is vertex form. Okay? Vertex form is f at x. Sometimes you guys might use different letters, but a x minus h squared plus k. Okay. The reason I showed you all three of these is, like we said, because I have to switch the y with the x. Well, there's two x variables. In standard form, we have two x variables. So it won't work in standard form. I'm trying to find the inverse. Factored form, I have two x variables again, so I can't just substitute y in for both of those. It won't be helpful. But vertex forms is important because in this form, there's only one variable x. Okay? So in other words, we need to take this from standard form, which it's in right now, to vertex form and then invert the function. In order to do that, we need to do something called completing the square. Okay, and we're going to go over that now. So hopefully you remember. If not, you're going to have to look it over, but I'm going to go a little quickly through this. When completing the square, and technically, I'm going to relate this to standard form just to give you an idea. Y equals squared plus x. This is my a. B, I kind of wrote that backwards. C, oh, it's very backwards. Hold on. Plus bx plus c. Okay. If you quickly notice, this is my a term. This is a b term, and we don't really have a c term. The c term is, you could say plus 0. Okay, you could say it's technically plus 0, but for what we're doing, we don't need it. Very first step to completing the square, what we do is we find out what the a term is, and we divide the very first two variables, essentially the x squared and the x, by the a term. Well, in this case, the a term was 4, so we're going to divide both of these by 4, almost like a common factor. That common factor 4 comes to the outside of the brackets, okay? And then we're left with what's inside. Well, we're left with x squared minus, technically you could say that's a 1. So it's 1/4 x. Okay, and we don't need to put the plus 0 in. The reason we do this is so we're setting up a perfect square trinomial is what we're trying to do. Or in other words, our a value right now is 1. That's our goal for this. This is our new b term, you could say. Okay? And there's a little side calculation. That b term, we put it into a little equation. We need to divide it by 2 and square it. Okay, it's a side calculation when completing the square. The reason we do this is, again, to create a perfect square trinomial. So I'm going to take 1/4, because that's my b term now, divided by 2, and square it. Well, we do what's inside the brackets first. It's going to give you a shortcut. When you're dividing a fraction by a number, you essentially just multiply the two bottom ones and keep it on the bottom. Okay? And it becomes 1/8 squared. Okay? We still got to keep going. An 1/8 squared is going to be 1/64. Okay? So this is important because we need this term. We actually need to add and subtract it inside those brackets. Okay? The reason being, if we add and subtract that, it's like, well, adding 0. It's not changing anything. 4x squared minus 1/4 x. And we're going to add 1/64. And we're going to subtract 1/64. Okay? But what we want to do is we actually want to take the negative 64th to the outside. And in order to do that, we need to multiply by the a term. Okay? So it needs to be multiplied by our 4 when it comes to the outside of the brackets. So when I multiply to the 4, just because of, think of distributive property, right? This 4 tactically needs to be distributed to every term inside the brackets. So if I'm to take one out and take it to the outside, I need to make sure it does get that multiplication. So this now becomes y is equal to 4x squared minus 1/4 x plus 1 over 64. Now 4 times negative 1 over 64 is negative 4 over 64. Does that make sense?
Yeah.
Yeah, negative 4 over 64. And that can be reduced. Do you know what that can be reduced into?
1 over negative 16.
Yes, great. So let's do that. Y equals 4x squared minus 1/4 x plus 1 over 64, negative 16th. Now, you could go about factoring this, but because we've created a perfect square trinomial, all I really have to do is find the square root of the first and the last term and bring down the equation of the middle term to put this into vertex form. So what I mean by that is this becomes y. Our 4 still stays the same. What's the square root of x squared?
X.
Yeah, square root of 1/64th. Think of it like you're square rooting the top term and square rooting the bottom term. What's the square root of 1?
1.
Square root of 64?
64.
You're thinking too much. What is 8 times 8?
8 times 64.
So what's the square root of 64?
8.
Yeah, that's right. So it's 1 over 8.
Okay.
Okay, so you just square root the top term and the bottom term. We bring down the middle term, which is our negative, and we square it. If we go into depth about factoring, I can explain that more. Just maybe go back and look over that stuff there. So now we're left at and a 16th. Well, this is the vertex form, right? Here's our A, our H, and our K of our quadratic. What's great about this is now I have one y and one x variable, so I can work about finding the inverse of the function. I'm going to make a quick graph here just to give you an idea. This function is essentially has its x or its vertex at positive 1/8 and negative 1/16, so it's probably something like that. And because a is 4 positive, it goes upwards and it's stretched. So it's something like this. We know the inverse function is going to be flipped on like a 45, right? So, I don't know if I can do it on this here. Essentially, it kind of goes like that. Okay, it's going to do something similar-ish to that. Okay, not quite, didn't quite get flipped, but it's going to be turned sideways. So we're probably not going to end up with a function. Let's actually find out what it is, though, what that function will be. So let's invert these. This now becomes x is equal to 4y. So we've inverted the x and the y. Okay, this is the inverse function now. Minus 1/8 squared minus a 16th. Well, now that we've done that, we can set this back equal to x. Starting with the 16th, we move it over. X plus 1/16 equals 4y minus an 1/8 squared. I need to move that 4 next, so I'm going to divide by 4. We divide both of those by 4. When I do that, this essentially becomes, let me think quickly. Yes, this becomes x over 4 plus, we can multiply the two bottom terms, so 1 over 64, okay, equals y minus an 1/8 squared. To move the square root, or sorry, the squared, we square root both terms. So now we're left with the square root of x over 4 plus 1 over 64, okay, is equal to y minus 1/8, okay. And when I move the 1/8 over, we're going to get root x over 4 plus 1 over 64 plus 1/8 equals y, okay. To relate this to a transformation, I'm going to actually factor out the 4th in here. Okay, I'm going to factor out a 1/4 just so we bring it towards our transformations. We're used to looking at something like k. Well, this becomes the root of a 4th times x plus a 16th. Okay, that looks a little more like our x is normal, and plus 1/8 equals y. And what I mean by that is, if you remember, I'll bring the y to the other side because we're used to seeing y over there. Can I do that? No, I can't do that. I'll just write it over here. Y is technically equal to this. If you remember our transformations, we usually have an a term, which deals with stretches. The function, in this case, the function is a root, so I'm going to just write it like a root. X, sorry, that's a k. K, x, is it c in this case? I think they usually write c as the letter.
Opposed to.
I think d is the other one.
Yeah.
Yeah, get rid of that. And then plus d. Okay, so this is the function that lets us know things. Well, in this one, this would be our a. It's essentially 1, doesn't change anything. Our k is the 4th. Our c is the 16th. And our d is 1/8. So if we were to graph this, we know that this function, because remember, this is this function here. This function needs to be written, if we were to write it, when we to graph it, because we have 16ths and 8ths, it's a little harder. If you remember writing this function. When we normally write y is equal to root x, 0, 0, and then 1 and 1, and then it's all the way at 4 and 2. 4 is 1, 2, and then 9 and 3, something like that. So we have something like this. Well, this function has now been shifted up an 1/8, right? That's what our d is. Shifts it up an 1/8. It's moved, because it's positive, to the left 1/16. Okay, c moves our, so it moves to the left a 16th. So we'll kind of go through each of these. Up an 1/8. Then that guy's been moved to the left the 16th. Still very close. And then it's been horizontally stretched by a factor of 4. So it's being pulled. Okay? Sideways. So it looks something like this-ish. Okay? Now, the problem with this is, technically, okay, this is the original, so let's zoom back in here, we'll go to 100. We're actually started with this function here. And the inverse of this guy is essentially tilting him on a 45. Like we said, it's going to be something like this, and it's been stretched, right? It's something over there. But because this quadratic is a full function, it's actually like this. Is this considered a function? No, this is not a function because it doesn't pass the vertical line test. We could have told that really early on by just looking at this once we graph the quadratic in vertex form and been like, well, we know when this flips, it won't be. But maybe the question actually wanted the formula, and we actually went about finding the formula of the inverse. That's the formula of that inverse there. Okay, so quite a bit of work there for that one.